today I would continue with the tight binding method, which describes the electronic states in periodic solids. And indeed, we would start with the simplest examples, like a linear chain of one type of orbitals with a given symmetry, like s orbitals or later on p orbitals, which can be already, the p orbitals can be oriented either parallel or perpendicular to the axis of this linear chain. So last week we defined some conditions which the wave function must satisfy if it describes the states of electrons in a periodic crystal. And we said that this function must satisfy the Bloch theorem that postulates that the function must contain some exponential part, and then a function u which is periodic with the same periodicity of as is the periodicity of the crystal lattice. And it can be in 3 dimensions, but we can simplify the problem and consider only 1 dimension. And this Bloch function can be constructed in different ways. We can use the plane wave basis, but we can also use this tight binding method, where each Bloch orbital, which is the equivalent of atomic orbital in molecules, and we know that in molecules the atomic orbitals are used as a basis to construct the single electron wave function in a molecule which is called molecular orbital. And Bloch orbital is in fact an analogy to atomic orbital, and it is a sum over atomic orbitals centered at the individual sides. So in 1 dimension we have the atomic orbital sitting on the side which is indexed n. So the x coordinate is in fact referred to the position of a given atom in the crystal lattice. So a is the lattice parameter, and n is just an index which defines the corresponding unit cell in a periodic 1-dimensional crystal. But in order to satisfy the Bloch theorem, these atomic orbitals, which are summed over all sides or over all unit cells in the crystals, must be multiplied by this exponential form, and this exponent contains the complex unit I, then the k vector, which is, but in this case it's just a number because we are in 1 dimension. And Na is the positional vector of a given unit cell. So in 3 dimensions, this exponential part would be slightly different, and it would be exponent, and then I, the complex unit, then k, which is in 3 dimensions a vector with 3 components, times Rn, and Rn is the vector defining a given unit cell. So it's a lattice point, a vector defining the lattice point, and this would be multiplied by an atomic orbital which is centered at this side Rn. Yeah, in this case, the atom would be sitting in the lattice node, but we could also add some fractional coordinates. So let's say another vector which defines the fractional coordinate within this unit cell. So we could define it as plus t or minus t, because the minus t because the coordinate vector r, which is the coordinate of an electron, is referred to a point where the atom is positioned, and if Rn means the vector of a given unit cell, and this t vector would be the fractional coordinate vector within a given unit cell. So this would be the extension of this definition to 3 dimensions. And okay, and we already know that the k vector must run from minus pi over a to plus pi over a, which is the Brillouin zone in 1 dimension. So we have an interval with the center here, which is called a gamma point 0, the origin of the reciprocal lattice unit cell or first Brillouin zone, and the boundaries of the first Brillouin zone is pi over a and minus pi over a. Okay, so within this interval, within the first Brillouin zone, we have to present the results of the electronic structure. That means the band dispersion, and also for each k point within this first Brillouin zone, we can define the eigenvectors if we have more functions. But now we start with only one function, which is directly the Bloch orbital, and we don't have any combination with other Bloch functions as yet. So let's start with this simple example. Now the orbital has a different form if we are at the origin of the reciprocal unit cell of the first Brillouin zone at k equals 0, and in this case it is just the sum of the atomic orbitals, because in this case k is equal 0, so this exponent is in fact the e raised to the power of 0, so it's equal 1. So we have a simple sum of the atomic orbitals. And if we now consider, and that's why it is called tight binding method, that we consider only the interactions between the nearest neighbors. So the orbital at the node equals 0 interact with +1 and -1 and nothing else. So we see that this state is completely bonding, and we can expect that it will have the lowest possible energy. Now, if we move in the first Brillouin zone to the Brillouin zone boundary, which is either pi over a or minus pi over a, this is referred to as a point x, we have again these atomic orbitals, and we sum them over all or unit cells. But now we have we substitute pi over a to here, so a is cancelled and we have I n pi, and this now depends on whether the n is odd or even. If it is even, then we have plus sign of this exponential function, while it is odd, then it is minus sign. So this exponential at the edge of the Brillouin zone changes the sign depending on whether we are in the odd or even unit cell. And again, if we consider the nearest neighbors interactions only, we see that there are only anti-bonding interactions. The color means the sign of the wave function. So the s orbitals is positive everywhere, but if it is multiplied by -1, it is negative everywhere. So if I plot it here, if we consider the s orbital on one node, let's say 0, then it has this form, and if it is taken as minus this orbital, then the wave function looks like this, so it is negative. But this positive or negative sign depends on whether we are at the 0 or 1 or 2 or -3 and so on. So depending, or just based on these considerations, we can plot the energy versus the k vector or k number. So for the most bonding states corresponding to gamma equals 0 or k equals 0, which is the point gamma, we have the lowest energy and the same sign of the wave function in each unit cell, while for the first Brillouin zone edges we have the highest energy, meaning a completely anti-bonding state. Okay, now if you look at other type of orbitals with different symmetry, the bonding and anti-bonding character can change. If we consider the p orbitals which are oriented along the linear chain axis, then if we are at the gamma point, that means all p orbitals have the same sign, no matter whether we are in even or odd unit cell. The interaction between the nearest neighbor slopes are anti-bonding. So we are at the highest energy with the completely anti-bonding state if we are at the gamma point, while if the atomic orbital changes the sign depending on a given unit cell, which is the case for the edges of the first Brillouin zone, we have a completely bonding interaction between the nearest neighbors, and that's why the energy is the lowest one. Indeed, you can ask why we observe this particular shape, which is actually a cosine or sine function, cosine function. But this must be analyzed separately, and we really need to calculate the energies of these states as a function of the k vector. So how can we do that? So we can consider the energy. If we have only one wave function, which is the case here, we have only one Bloch orbital, the energy is defined as an integral, and now the Bloch orbital Hamiltonian, which contains the kinetic and potential energy, and the same orbital, and we integrate over the whole volume. So we have the same function here, and this expression means that we apply the Hamiltonian on this wave function, and then we multiply from left. The result of the application of Hamiltonian into this wave function is multiplied from left by the same wave function, and the result is integrated all over the space. In fact, we should divide it by the so-called overlap integral, which is square of this function. But now it depends on whether these Bloch orbitals are orthogonal, or the atomic orbitals forming these Bloch orbitals are orthogonal or not. If they are assumed to be orthogonal, then it means that the overlap is equal to 1 if the same atomic orbitals are considered, and it is equal to 0 if we apply this integral for different orbitals sitting on different sides. But let's define it in this general form. If we neglect the overlaps between the nearest neighbors orbitals, which are numerically relatively low, then this integral is equal to unity. Okay, so now we can substitute the corresponding Bloch orbitals into this integral, and if we do that, we have, okay, the energy is equal, now the integral, and then now we have sum over all atomic orbitals. Let's denote them chi n, and we sum from n from minus infinity to plus infinity. And then we have e to the power of a k n a. And now we apply the Hamiltonian on the same function. So again, the sum for all n, psi n, and a e to the raised to I k n a. And we integrate over the whole volume. Now this energy would be referred to the whole periodic crystal, but we can also refer the energy to a single orbital or single unit cell. So we can consider only the chi0 orbital, and this chi0 orbital is overlapping only with its nearest neighbors. So let's say if we divide this by 1 over n, where n is the number of atoms in the periodic chain, which can be infinity, in fact, for an ideal crystal, then this integral over all, considering the sum of all atomic orbitals multiplied by this exponential factor, is equal to an integral considered only for the chi0 orbital, for the only one unit cell and its nearest neighbors. So it would be, let's say, chi minus 1 and exponent, and now we subtract, actually we multiply the exponents of the unit cell 0 and n minus 1, which results in, because if n is equal 0, we have no number in the exponent for the chi0, so it is just minus I k a h, and now we apply this to chi0 without any exponent already, and the second integral would be chi0 h and chi1, and now again in the exponent we have now I k a. And again we integrate And so now this, because this doesn't contain this part of the wave function or of the integrand doesn't contain the positional vector of an electron, so it can be put in front of the integral. So we have, and then we can define, so we have chi minus 1 h chi 0 integral and dv times a minus chi a plus chi 0 h chi n dv and this, okay, and this integral is equal to this so-called transfer integral. So the transfer integral means, sorry, I forgot one term. We still have another integral here, and it is the interaction of a given orbital with itself. So it is chi 0 h and the same orbital. And this first part is equal to the energy E0 of the original atomic orbital plus, and this integral is equal to t, and this one is equal also to t. And it's a measure of covalent interaction between the nearest neighbor, and it is called resonance or transfer or hopping integral. So now we can express, so we have this, and we can express the energy E as E0 plus T, and then in the parentheses we have IKA plus E minus IKA. But this can be expressed as cosine Ka plus I sinus Ka, and this can be expressed as cosine Ka minus I sinus Ka. So the complex parts of the wave functions are cancelled, and we have only the cosine, the real part. So E0 is equal to 2t cosine of Ka. If we considered also this overlap integral in the denominator, it would be, I will write it, so, and the same function dv, and it is equal to chi 0 square dv, and then the overlap with the orbital in the unit cell 1 and with the orbital in the unit cell -1. So it is plus chi 0, chi 1. And chi 0, chi -1, and it's something like this. And this is equal to unity, and this integral, after disregarding the IKA, is equal to the so-called overlap integral. But usually this overlap integral is very low compared to unity, so it is sometimes neglected. But correctly written, it is 1 plus 2s cosine of Ka. And we should in fact divide the result obtained on the previous slide here by this overlap integral. But in these figures, this denominator, this overlap between the nearest neighbors is neglected. So we have only this form of the energy dependence on the k vector, and the t is this transfer integral. And if you substitute now 0 here for k, cosine of 0 is 1, and we have usually if the interaction between the nearest neighbors is bonding, then the t, this transfer integral, is negative. So we have E0 and minus 2 and the absolute value of t, while for Ka equal pi over a, it is cosine of pi, which is minus 1, and if it is multiplied by the negative number here, we obtain the plus sign. So in this case, we have the lowest energy for the gamma point, k equals 0, and the highest energy for the x point, which corresponds to pi over a. So once again, I will write it. So if the energy is by neglecting this term, if the energy is E0 plus 2t cosine of Ka, and if for the s orbitals where we have the same sign between the nearest neighbors, then t is less than 0, and for k equals 0, the cosine is equal 1. So we have E0 plus 2t, but if t is negative, we have the lower value, and for k equal pi over a, we have E0 plus 2t cosine of pi, which is minus 1, so it is E0 minus 2t. And again, t is negative, so we have a higher value. If we have the p orbitals, which at gamma points are oriented in this way with this symmetry, we have t greater than 0 for this nearest neighbors overlap, and we have the opposite dispersion. That means the highest energy is at the gamma point, and the lowest energy is at the x point. So this is the principle for the simplest cases. We could also consider the pi interaction between the nearest neighbors. From the point of view of symmetry, the pi orbitals, you see that there is an overlap of the same sign of the wave function between the nearest neighbors. Thus oriented orbitals behave like the s orbitals. And you see the dispersion. Sometimes for E0 we use alpha, and for t, for the transfer or hopping integral, we use beta. It depends on the textbook you read. And we can also have this interaction between the d orbitals in a given ring. And again, in this case, the d orbitals have similar symmetry as the as the p orbitals oriented along the chain, so sigma bonding. This is the pi bonding, but realized by d orbitals. Okay. And if we calculated the wave function for a given energy, so let's say here in the previous case we can select any point on this curve, and we might ask how the wave function would look like for a given k point. So we already know the simplest cases at the gamma point and x point. These are really the simplest cases because the wave function is real. It is either each atomic orbital is either multiplied by 1 or minus 1 at the x point, or it is just the sum of atomic orbitals at the gamma point. But the form of the wave function is more complex if we substitute an arbitrary value of the k vector, and the wave function is complex in general, and so we should visualize separately the real part and the imaginary part. But the point is that if you go from the point with the lowest energy to the point of the highest energy, the most anti-bonding, we gradually increase the number of anti-bonding interactions, and also the periodicity of the wave function increases up to the middle of the band, and then again decreases. So you see that in the middle of the band we have the periodicity 1, 2, 3, let's say, of the unit cell parameters. So for instance, we have a completely non-bonding character. In this case, you see that there are both anti-bonding and bonding interactions between the nearest neighbors. And gradually the number of anti-bonding interactions increases when you go from the bottom of the band corresponding to the most bonding state to the top of the band corresponding to the most anti-bonding state. You could also note that the bandwidth, which is sometimes denoted as W, in this case is 4T. So the greater is the parameter T, which is the measure of the covalent interaction, the larger or the broader is the band. So typically for good overlap between the nearest neighbors, we have also the high value of T and the broad band. While if the overlap is relatively low, then the bandwidth is also very small. Okay. So now we could already extend this concept from one-dimensional crystal to three-dimensional crystal, but still we would only consider the same type of atoms and the same type of orbitals each unit cell. Here we have a generalization to two dimensions. So each orbital within a given unit cell has 4 nearest neighbors, but indeed for a three-dimensional cubic lattice it would have 6 nearest neighbors. And the corresponding band would be also larger. So, and we would need to plot the energies within the first Brillouin zone, which is also for a simple cubic lattice. It is the first Brillouin zone is also a cube. Okay, so now the alpha is the so-called on-site energy of a given atomic orbital, let's say E0, and beta here is the t, this is the transfer or hopping integral. So in one dimension we have this form, but in 3 dimensions you see we have 6 terms of this type, but we can always combine the terms which have the same kx or ky or kz, the same component of the k vector. We can use the Moaver law and express this exponential parts as a sum of cosine and sine, where the sine part is actually complex and it contains this complex unit I. But the signs are cancelled in this case again, so we have 2 beta or 2t, and the cosines of kxa, kya, and kza. So we considered the cubic unit cell with the same a unit cell parameter in all 3 dimensions, and this is the resulting form of the energy, in fact. Okay, and how could we plot then the band dispersion? So we know that the first Brillouin zone looks like a cube. We have the gamma point at the center. Then we have the x point here in the center of the face. Then we have the M point somewhere here. Then we could either go to gamma point, back to gamma point, or to go to the R point, which is here, and then back to the gamma. And I think this part is symmetrically equivalent with all the other, I don't know what it is, an octant of the cube, I think. So we could plot the band dispersion, let's say from gamma to x to M, then to R and back to gamma. And we would have the lowest energy for the gamma point, I think. It would be E0 minus, now it would be minus 6t, because we would have, okay, in this case it would be, t would be positive, but if we consider the s orbital, we would have plus 6t, but the t would be the t would be negative. And then at the R point, we would have probably the highest energy corresponding to E0, or here we would be E0 minus 60, with t being negative, so we would have the highest energy here. So and it would look like something like that, and then back to gamma point. So we have the bandwidth, which is 12t, and the larger is the t, the largest is the band. Okay, so far we just considered one type of orbitals, so we have only single Bloch orbital, and we didn't have to combine the different Bloch orbitals to obtain the so-called crystal orbitals. But for this general case, we start with the basis functions, which are the Bloch orbitals, and they contain a given type of atomic orbital, and we sum over all unit cells. And here it is already defined in 3 dimensions. So we have the scalar product of k vector and the Rn vector of a corresponding unit cell. But now, if we have more types of orbitals within the unit cell, we have to combine the Bloch orbitals like the atomic orbitals of in molecules are combined to obtain molecular orbitals. So this is a complete analogy. So we make a linear combination of Bloch orbitals and we obtain the crystal orbitals. And what we are interested in, or what we want to know, are the energies as a function, which means eigenfunction as a function of k. So we would like to know the band dispersion, but for each k point, we also need to know the coefficients in this linear combination. And in order to find both the eigenvalues and the so-called eigenvectors, which are the coefficients for each energy, we need a set of these coefficients, which is denoted as an eigenvector, a set of coefficients in this linear combination. And in order to evaluate the eigenvalues or obtain the eigenvalues and eigenvectors, we need to solve the so-called secular equation, or to apply a so-called variation method. This is in brief shown here. We have to solve a set of homogeneous linear equations for these coefficients. But in addition, we don't know these eigenvalues, which are here as parameters for the unknown coefficients. But because we are dealing with a homogeneous set of equations, in order for the solution to be non-zero, the determinant of this matrix must be equal 0. So first we set the determinant of this matrix equal to 0, and we solve for the unknown values of energies or eigenvalues, and then we substitute the individual values of energies and we solve this homogeneous set of equations for the unknown coefficient, that means the eigenvectors. And in this matrix we have the matrix element called H, which have this form, and these are the integrals, where this is the effective Hamiltonian containing the kinetic and potential part, and we apply this Hamiltonian on the given Bloch function, and we multiply from left by generally another Bloch function. If we are dealing with the diagonal element, so J is equal L, then this and this wave functions are the same. But if we want to evaluate the off-diagonal element, then phi j and I are different. And this must be done for all values of k vectors within a given Brillouin zone. So we must select a mesh of k points, and we have to solve. And these are in fact the integrals. This is the so-called Dirac notation, and so this means in fact an integral of phi I h phi j over the whole space. But again, within these Bloch functions, we consider usually only the nearest neighbors for the atomic orbitals. If it is a complex function, then this function must be the complex conjugate of the original wave function phi I, which is denoted by an index star. So the whole problem is in fact reduced to the evaluation of this type of integral and possibly also the so-called overlap integrals, which are defined as phi I, phi j, dv. And again, in these overlap integrals, which are these SJL values. In these overlap integrals, we consider again the overlaps between a given atomic orbital itself, which is equal to 1, and then between the nearest neighbors at maximum. Okay, so just to recall you to how this secular equation or set of equations is derived, it is shown here. So first we consider the wave function as a linear combination of some basis functions. So this function, like the crystal orbital or molecular orbital, is a linear combination of Bloch orbitals or atomic orbitals for molecules. Now we substitute to the Schrödinger equation, so we have this linear combination here, and on the right hand side we have an unknown value of eigenvalue, the energy, multiplied by the same wave function. Then we multiply from left by the corresponding basis functions. So we get such a set of equations. Then we convert it to a matrix representation. So from this set of equations, we have a matrix which contains these matrix elements times the eigenvector, and on the right hand side we have the energies multiplied by the matrix elements of the overlap matrix, and again multiplied by the eigenvectors. Then we move this right hand side to the left, so we obtain only a zero vector on the right hand side, and we have two matrices multiplied by the eigenvectors on the left hand side, but because the eigenvectors are the same, we can extract them and we can join the two matrices together, and we end up with this form of the set of secular equations where we have these matrix elements H and S, but sometimes we neglect this S, which is then simplified, and because it's a set of homogeneous equations, this has a non-zero solution if the determinant of this matrix is equal 0. So from this condition, we are able to solve for the unknown value of energy, and if you evaluate this determinant, you see that if you start with two basis functions, you get the matrix 2 times 2. The dimension of the matrix will be 2, and the determinant is then quite easily evaluated. Sorry. So we have if we have a determinant of H11 minus E And I will neglect the S or the overlap integrals. Okay. And H22 minus E. So this is equal to the multiplication of the main diagonal, which is H11, H22 plus E square plus H12, H11 plus H22, and it is with the minus sign here. And E, and this is equal to 0. So we have a quadratic equation. We must subtract the second diagonal product. So it is H12 times H21. But because the matrix must be so-called Hermitian, these two matrix elements must be complex conjugates. If these are the real numbers, they are equal to each other. If they are complex numbers, it is if H12 is equal A plus IB, then H21 must be equal A minus IB. So these two are complex conjugate, which means that A12 is equal to A21 complex conjugate. Okay. So, and because in this case we have the quadratic equation, we get two solutions, two eigenvalues, and for each eigenvalue we get the different set of coefficients of the eigenvectors. So we first substitute the one energy into this set of equations, and we solve for unknown values of C. And then we substitute the other eigenvalue, and we get another set of coefficients, another eigenvector. In the current computer algebra systems, this secular problem is implemented. So you just define the matrices and you type eigenvectors or eigenvalues, and you get the results immediately. So the programs, the computer algebra systems are able to solve this eigenvalue problem for you. And I will show it later on an example of two Bloch orbitals which are combined to form the crystal orbitals. But let's continue with the simple linear crystal, but now let's consider two atomic bases, or diatomic bases, which means that we have a doubled unit cell and we have two atoms and two orbitals within a given unit cell. So in the simplest case, where both orbitals have the same energies, so E is equal E1 and equal E2, and also the transfer integrals within a given unit cell and with the neighboring unit cells is the same. So in this case, we just obtain the energy which is equal to this expression, and it differs from the previous case only in this argument of the cosine function, which is k over a over 2. And this means, in fact, that the unit cell, because the unit cell was doubled, the first Brillouin zone is decreased by 1, is decreased by a factor of 2. And this means that the band dispersion for the original unit cell, which was half of the current unit cell, would look like this, but because we enlarge the unit cell, we have twice smaller first baryon zone, and we have just folding this part of the energies to the new first baryon zone. But still, these states at the edge of the new baryon zone are doubly degenerate. So these two bands touch each other. But this is in fact not very interesting, because if we have the same energies and the same transfer integrals, then there is no reason why not to consider a smaller unit cell, as in the previous case. You see that here we have at the gamma point, we have two wave function. One is completely bonding and one is completely anti-bonding, corresponding to this point and this point. In fact, we could consider two dimers, one with the plus sign of both orbitals within the unit cell, and another one with plus-minus combination of the two orbitals. It is similar as the construction of so-called symmetry adapted orbitals in molecular orbital theory. So we consider two symmetry adapted orbitals within the given unit cell, and then we combine them, and the resulting at the X point, we have something which is both bonding and anti-bonding. So the resulting state is non-bonding, because we have plus-minus interaction, which is anti-bonding, and plus-plus interaction, which is bonding. So the bonding and anti-bonding interactions are cancelled, and we are at the original value of the energy of the atomic orbitals. But now let's release these parameters such that we first consider the same energies but different transfer integrals, or the same transfer integrals but different energies. And this is shown, no, not yet. This is just an example of orbitals of different symmetry. If we consider the orbitals which are anti-bonding at the gamma point originally and bonding at the X point, we have the opposite trend. But in fact, the resulting picture is the same as the band dispersion is exactly the same as in the previous case. But now consider this example where we have first, we have, let's say, the displacement of atoms within a given crystal, which is actually a very frequent case. If you consider the linear chain of s orbitals of hydrogen atoms, then you would actually observe exactly this situation, because you see that the hydrogen atoms can't withstand or can't form a state where they are equidistantly spaced along the linear chain. You would always observe that forming the dimers, that means the molecules of hydrogen atoms, hydrogen molecules. And this can be interpreted as a formation of the superstructure with the doubled unit cell. And because now there are two kinds of, or two distances between the nearest neighbors, one within a given unit cell, which is shorter, and we have, that's why the higher transfer integral, T1, and one longer between the nearest neighboring unit cells. where the distance is larger, and that's why the T2 would be smaller in absolute value than T1. So again, we have two Bloch orbitals, one of this type. So within a given unit cell, we have this atomic orbitals, but this side is empty, while the second Bloch orbital has an atomic orbital here, but this side would be empty. And so this is a two-dimensional problem, and we would need to define the four matrix elements, and we could consider again the nearest neighbors interactions. So let's consider first H11, which is the first Bloch orbitals. Let's say this integral and sum and chi a n h and the same orbital this type, and this can be simplified as the interaction of the given orbital in the zero unit cell by itself. So it is chi 0a h chi 0a, the same one, which is the energy EA. But now what we have more, I think nothing else. No, nothing else, because it is shown here. It is really only because if this orbital interacts with itself, we have only this matrix element. The same applies for H22. It is just the energy of the b orbital, but the off-diagonal matrix elements are, let's say, integral, and now we have A0b. So this is the interaction within the unit cell. But then there is another term where this orbital 0a interacts with the A, let's say -1b, but this -1 has an exponent minus I k a, and I will finish this. So it is equal to the transfer integral t plus t e to the minus IKA. And for the second matrix element, H21, we would have an interaction of the chi B0 with the chi A0 in the same unit cell, so again T, but then with the chi 1b, chi 1a, so it would be plus EKI. So you see now that the hermicity of the Hamiltonian matrix is satisfied, which means that this matrix elements and this one are complex conjugate, because if there is a minus sign here at the complex part, it must be plus sign here at the diagonal element, which is symmetrical with respect to the main diagonal, which results in the real values of the energies, because they must be real. And this is just due to the fact that if we multiply in the evaluation of the determinant of the matrix, if we multiply H12 times H21, we have, what do we have? We have, I think, T square, and then 1 plus and 1 plus a to the minus. And if we multiply these two parentheses, we would obtain 1, then these two yield 1 as well again, and then what else? We would have no, 2 times, no, we would have this plus this, but here the complex parts are cancelled and we obtain 2 times cosine of Ka. So you see that the resulting product of two matrix elements, which must be evaluated when we want to evaluate the determinant, yields the real number, which is important because the energy must be real. And if we do that for the this two-dimensional problem, we can solve the quadratic equation quite easily, and we obtain the resulting value of energy, which is defined here, and this is the average of the two on-site energies here. Then this is the square of the difference of the two energies divided by 2, and then there is this this part which results in from the off-diagonal matrix elements multiplication. Here we consider different values of T1 and T2, a more general case, while here I consider the same parameter T. So this was just to show you that we obtain a real number, but indeed we would, in this particular case, we would need to consider two different transfer integrals. And if the on-site energies of these two orbitals were the same, then we would have 2 times E over 2. So for the first case, if E0 is equal E, let's say 0A, and it is equal to E0B, the on-site energies of the atomic orbitals. From this, we would obtain E0 plus minus, and then square root, and here this part, sorry, this part will be equal 0, because if the energies are the same, then this difference is equal 0, and we would have only this part in the under the square root. So T1 square plus T2 square plus 2 times T1 T2 cosine of Ka. Oh, sorry. Okay, and for the second case, if we have different energies but the same transfer integral, it is a0 plus a b0 over 2 plus minus, and then again square root, and a0 minus a b0 over 2 and the square of it. But then if T1 is equal to T2, we have 2t square and 1 plus cosine of Ka, something like that. And these two particular cases are very important because they demonstrate two kinds of insulators. In fact, in both cases, in the first case where the energies are the same, but the transfer integrals are different, which corresponds to this so-called cooperative atomic displacement, then the equidistant atoms form molecules, or they are approached or moved away from each other. And this case results in opening of band gap between the valence band and the conduction band. So this distortion or forming a supercell due to cooperative atomic displacement results in opening of a band gap. And if we have 1/2 of electrons, it means that this band is completely filled and this one is empty. So we obtain an insulator or semiconductor. And this would be the case for a ring of or linear chain of hydrogen atoms, because each hydrogen atom contains 1 electron. So we would have this band, which would be filled by two electrons, because this band corresponds to 2 hydrogen atoms per unit cell, which are now, but this band can accommodate only 2 electrons, because each of these levels can be occupied by 2 electrons with opposite spin. So this band would be completely empty, while this band would be this band would be filled and this one would be empty. Now the second example or second case is the case of ionic formation of ionic insulator, and the ionic insulator is characterized by very big difference between the energies E01 or E0A and E0B, because if we have an electropositive atom, it would have a higher value of let's say E0A or E1 here, and if it is combined in a linear chain with a very electronegative atom, this electronegative atom would have a very low value of E0B or E2. But we would have an overlap between the electropositive or electronegative atom between the nearest neighbors. That means the transfer integral would be only one type, T. And in this case, we obtain this kind of energy, this one which I have derived. So it is okay. We have to check whether there is this factor 1 here or not. 4t square, I'm not sure whether it is. If we go back here, then we have t square and here 2t square. I would say that I have correctly written this part. I'm not sure, but I would guess it is correct. Well, this wouldn't be correct, probably. Perhaps they considered some relations between the goniometric functions, because here we have Ka over 2. So probably it can be arranged into this form. But again, the band gap is open between the valence band, which is filled, and conduction band, which is empty. So now let's imagine we have a chain of sodium atoms and chlorine atoms with the corresponding valence orbitals. So sodium brings 1 electron and chlorine also 1 electron. But if the band structure is like that, this band is completely occupied. And because the corresponding coefficients in the linear combination of the wave function of the Bloch orbitals would be higher for the more electronegative atom in this band, while for this valence conduction band, we would have a higher weight of the sodium atom or more electropositive atom. But these states are empty, but the occupied states are more represented or more are dominated by the orbitals from the more electronegative atoms, and that's why we have a shift of electron density from sodium atoms to chlorine atom, and we obtain the ionic insulator. So this is this case of ionic insulator. And real examples are sodium chloride here. So we have a big difference in energy between sodium. This is already for 3 dimensions, and there is a big difference in energy, like 5 or 6 electron volts between the 3s orbitals of sodium and 3p orbitals of chlorine. So we have a small transfer integral and big difference in energies. So the bands, at least the valence bands, are relatively narrow and they are completely occupied. And this band is dominated by the 3p orbitals of chlorine with only a small admixture of sodium 3s orbitals. While the diamond is an example of the second insulator, the covalent insulator. Here we have 2 atoms per primitive unit cell, and there are probably different transfer integrals between these atoms and the atoms in the neighboring unit cells. But these transfer integrals are relatively large, and that's why we also obtain a large band. But we have a band gap between the valence band and the conduction band. So this is the second example. Now, a 2-dimensional example, that means we consider a plane with 2 types of atoms. One is more electronegative, like oxygen, and one is more electropositive, like copper. And this CO2 plane is present in high temperature superconducting cuprates. They are the conducting part of the crystal is planar, and it consists of the d orbitals of copper and the p orbitals of oxygen. In this case, we considered not only the nearest neighbor interactions, but also next nearest neighbor interactions between the p orbitals of oxygen, which are perpendicular to each other. But this is just an ingredient to the method. But important point is that we obtain from 3 orbitals. This is the basis, which must be extended into 2 dimensions, so that we obtain 3 types of Bloch orbitals. And these, let's say, dx² minus y² of copper, px of oxygen and py of the second oxygen. And these three Bloch orbitals are combined, and we obtain three bands, where two bands are predominantly of oxygen 2p character, and one band is of copper 3d orbitals character, indeed with a mixture of these oxygen p orbital states. And now we have the square planar first Brillouin zone with the origin, gamma point, x point, and m point, and we can plot the band dispersion along these principal directions of the first Brillouin zone, and we obtain the most for this band we obtain the most anti-bonding states for the M point, while in this this band of predominantly oxygen character, this is the most bonding state at the M point. While at the gamma point we have a completely non-bonding character of all bands. And for the specific points in the first Brillouin zone, we can also plot the wave function as combinations of the Bloch orbitals. So we see that here we have for this state corresponds to this bonding interaction between the d and p orbitals along the x direction, which is completely bonding, while here we have the opposite signs of the wave function for this state, which means that this state is anti-bonding. But we have no interaction in this y direction. But if we move to the M band, M point of the first Brillouin zone, we see that this state corresponds to completely anti-bonding interaction in both directions. While here we have, no, I think it is opposite. No, it is like that. We have one completely bonding interaction here, and this interaction is nearly non-bonding because we have a bonding interaction in this direction. No, it is. You see, here is an anti-bonding interaction, here is a bonding interaction, so it is a combination, in fact. That's why we have nearly non-bonding state here. The last example is the graphene plane. Indeed, we would need to consider both sigma bonds and pi bonds, but this example is just a fragment consisting of pi orbitals which are perpendicular to the planar hexagonal structure of the carbon atoms in graphene. Graphite means the three-dimensional structure where we have these planes, like these ones, but they are stacked along the C direction of the hexagonal unit cell, and there are only weak interactions between the individual planes. But in graphene, we have separated a single plane, so we have no interaction in the C direction, and we consider only the interactions within this single plane. But if you look at the plane from top, even if you have these pi bonding where the orbitals are oriented perpendicular to the plane, you see only, if you look at it from the top, you see only the signs of these slopes, while you don't see the lower lobes. So it looks like s orbitals, but here we have the upper lobes of the p orbitals oriented perpendicular to the axis. Here the formulation of Bloch orbitals is a little bit more complex because we have one atom at the position 2/3 and 1/3, and another atom, and that's why the corresponding atomic orbital is at 1/3 in one direction and 2/3 in the other direction. So we must write the corresponding Bloch orbitals in this way, and because we are in 2 dimensions, we should have Ka and Kb. We should have Ka and Kb, in fact, yeah. Which is probably there is a mistake here. There should be Kb here, Ka here, and Kb here. But now these 2 Bloch orbitals are combined, forming the linear combination of the crystal orbitals. And again, we don't know the energy, and we don't know, for each energy, we don't know the coefficient C1 and C2. So we have again evaluate the matrix elements. Again, as in the previous case of linear chain, the diagonal matrix elements contain only the interaction of a given orbital, atomic orbitals with itself, but the off-diagonal matrix elements, which are complex conjugate, involve this dependence on the k vector. And if we evaluate the determinant, we must obtain the real function, which is put equal to 0, and we again solve this quadratic equation, and we obtain this form of energies. But because we have only one transfer integral, and E0 is the energy, on-site energy of the original atomic orbital, the resulting band dispersion has this form. The first Brillouin zone is this hexagon, while the primitive unit cell in the reciprocal space or reciprocal lattice has this form. But this endpoint is, I think, equivalent to some point on this joint line between gamma and L. So, and the band dispersion looks like this. At the gamma point, which is here, we have one completely bonding state and one completely anti-bonding, because each orbital has the nearest neighbors of the opposite sign. So we have these 2 states. But for the x point, we have 2 bonding interactions here and 1 anti-bonding, while here we have again 1 bonding and 2 anti-bonding. We have 1 bonding and 2 anti-bonding. So the difference in energies would be smaller, because the bonding and anti-bonding interactions are partly compensated, and that's why we have this gap at the x point. At the m point, we have the same energy, so apparently the x and m points are symmetrically equivalent. But interestingly, at the L point, and it is very important, at the L point, we have, no, it is not shown here, but at L point, we have a completely non-bonding interaction, which means that in this equation, these terms must be cancelled. So we have apparently 3, and these cosines would give minus 3/2 probably, or 3/4, I don't know. Anyway, this term in the parentheses must be cancelled, so we obtain the original value of E0. We can substitute it for the L point and check whether it is really really 0. So, and this is a particular characteristics of graphene layer, that it is in fact not an insulator, because due to symmetry at this L point, the valence and conduction band touch each other. At the Fermi level of the whole graphene layer, these states are really at the Fermi level. So these are the highest lying states. The electrons from here can be excited to the conduction band, and that's why graphene and graphite as well is a conductor. But it's not a real metal, because in real metal we would have a partly filled this band. Now not in this case, we have a completely filled band and another band which is completely empty at 0 Kelvin. But at finite temperatures we have the excitations, because the band gap is 0. And this 0 band gap is imposed by symmetry. So I would just show how this problem can be solved in Maple, and I would then recommend to, because one of the tasks you will have, or one of the problems you get will be dealing with tight binding method, and you could use any computer algebra system like Mathematica or Wolfram Alpha or Maple or MatCat or something like that. But I know Maple, so I will show how it is solved in this case. And Maple is available. You can download it and install on your computer, but you must be in the domain of UCT Prague, so that it is a server license, and you have to input at the installation you have to input the IP address of the license server, and then if you are in UCT domain you are authorized and you can run your Maple program. So in Maple you always, if you want to solve the eigenvalue problem, that means you define the matrix elements, and then you solve for eigenvectors and eigenvalues. You must use this linear algebra package libraries which contain the functions necessary to solve this eigenvalue problem. So you press with linear algebra, and then you define this matrix which contains these matrix elements we have written over there. So if you look at the presentation, these matrix elements must be input into this matrix, and this is done here. It is called B matrix, and it has E0 on the main diagonal, but on the off-diagonal elements contain this Ka and Kb. This is shown here. I just expressed the exponents or e raised to the power of IKA at Ka by cosines and sines. Here is the complex unit I. Okay, so if you do so, you can then calculate the eigenvalues. It is just given in a general form with unknown values of Ka and Kb and T, But if you then substitute for E0, let's say equals 0, and T is the transfer integral, let's say 2 electron volts, and now you solve for gamma point, Ka0 and Kb0, you obtain these values, +6 and -6, which is 3, 2, plus and minus. You could also run the eigenvectors, and you would obtain both the this function, this subroutine calculates both the eigenvalues and the eigenvectors. For each eigenvalue, you obtain the set of coefficients in this linear combination. But if I want to plot the whole band dispersion, I have to define this set of k points, and this is somewhere here. This set of values, we have pi, 0, and then we run here and here. This is the Ka, the first component of the k vector. This is the Kb, the second component, and the third column corresponds to the distance. So I created just in Excel, and I summed from the beginning. I summed the distances between the nearest points within the first Brillouin zone along the principal directions. So you see that here the first point corresponds to the difference between the point pi 0 and 3 0. So it is 0.14. Then we continue to here, and it is 0.34. So we gradually sum the distances between the nearest points, so that we obtain the one-dimensional graph. But the program uses these two values, Ka and Kb, and it substitutes them into the eigenvalues which were calculated in before. So for this set of points, we would obtain the resulting energies, and this is then done here in this. So we read the data from the data file kvector.dat. Then we do some operations with this input data, and then we calculate for each k point we defined in the external file the corresponding eigenvalues, the energies, and then we can plot them. So we can also write them in an external file and plot them in a separate plotting program. This is shown here, but we can also plot them directly here. And because we have two bands, we create first graph for the first band and the second graph for the second band, and then we plot the two graphs together. The only issue is here that we didn't exactly define, in our list, we didn't exactly define the L point where the two bands touch each other. That's why we have this artifact here, but we should observe the touching the two bands here. So that's, and if you define your own matrix here, you must derive it by considering the corresponding nearest neighbor interactions. So if you derive the individual matrix elements, you can then define this matrix and just solve. If you install Maple program, I will provide you with this example so that you can just redefine these matrix elements or this Hamiltonian matrix for your particular case and then solve it and plot it as you want. I would also like to extend this problem or this program in order to calculate the density of states according to the formula I have shown in last week. So we would be able to plot the band structure along the principal directions of the first baryon zone. But if we define a mesh of K points within the first baryon zone, or an irreducible part of the first baryon zone, we would be able to sum all eigenvalues and calculate the density of states. And then we can integrate the density of states up to the Fermi level and evaluate the number of electrons, or vice versa. Gradually integrate the density of states up to the given number of electrons you have. And if you spend all these electrons, you hit the Fermi level. So this is another task which can be done.